Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be discussing rolling without slipping. So this is a continuation of the series of videos I've been doing on rotational dynamics and rotational motion. I guess we could begin by recalling a few things that have been covered both in this set of lectures and in previous ones. One of the major points is to recall is the rotational kinematics system of equations. So you got rotational kinematics, and I'm not going to write all the equations up. I'll just give like a simple example of one. Your delta theta is 1/2 your alpha, that's the angular acceleration, times time squared, plus your initial rotational speed times time, etc. Another thing to keep in mind is the conditions for rotational motion in general. So this would include centripetal motion. We'll just label it as centripetal. It's actually étale motion, as well as actually tangential motion. So centripetal, tangential, and a not exactly new term, but new to this context term, center of mass motion. So I'm going to actually draw a little picture here. Let's say that this is a wheel that is spinning about an axle, but it's like off the ground. So maybe it's like a bicycle that's been flipped upside down to put away for the day on a rack or something, and the tire is just kind of spinning around like this. This rate omega can be related to the essentially motion of this thing. This has a tangential speed by v tangential is omega times r. We also have a centripetal acceleration, which I'll put in purple. So we'll say A sub c. A sub c is omega squared r, which is also v tangential squared divided by r. Okay. What about the center of mass motion? Well, the center of mass motion would be if this whole object, rather than spinning about in place, let's say here's the center of mass, the whole object could be translating this way. And so if the whole object is moving together with some speed, then this would be the center of mass speed of the object. And that's true even, by the way, if the object is also rotating. And so actually this rolling without slipping condition involves putting these two ideas together. This idea of rotational motion along with this idea of center of mass motion. So let's combine these two things. Now this combination is in this case meant to be kind of arbitrary. So let's say that this thing happens to be rotating with some speed omega, and let's say that it is also moving forward with some v center of mass. So we might ask, for a given point on the wheel, what is the actual instantaneous velocity or speed for that point? Well, this point on the wheel happens at this moment in time to have a tangential speed v tan, which is represented by this little arrow. And so if I take these two arrows for this point, because the wheel itself is moving this way, and that means the point on the wheel also is moving this way, as well as moving in a rotation like this. That means that I have, as a collective motion, a center of mass motion, and then also a tangential motion, v tan. And so my total velocity for that one point at that one moment in time is given by the vector sum. So v total is equal to v center of mass plus v tangent, or tangential. It should be evident that the center of mass motion is the same for every point on the wheel, but the tangential motion is not. For example, if I pick, say, this point right here instead, then, at this given time, my tangential speed, or my tangential velocity, is actually more like this direction. And so I would have a totally different, we'll call this one like point 1 and we'll call this one point 2. Here's point 1. Point 2 will have a totally different outcome for the total velocity. I have my tangent here, and then somewhere over here, or excuse me, this is my center of mass. Somewhere over here I have my v tangent. And so my total for this point will actually point in this direction and have a shorter length. So v total, once again, is v center of mass plus v tangential. And so obviously each point on the wheel is going to have a different value for the total velocity. Now here's where the rolling without slipping comes into play. Let's again draw that same wheel. Again, I have my center of mass motion, v center of mass, and this time I pick a point that's right here on the ground, the one point of the wheel that's in contact with the ground. If you have a round, that is circular cross-section wheel that is non-compressible. You have this one point that's actually in contact with the ground. Well, the tangential speed, if we're rotating like this, omega, the tangential speed v tan will be here, and the velocities are in exactly opposite direction. Now the rolling without slipping condition is that the center of mass velocity is equal to, but opposite of, the v tangential velocity at point of contact. So we can say at contact. Okay, put differently, that means that v center of mass and v tangent at point of contact are both omega times r, where r is again the radius of our wheel. Okay, now the reason why this is important is that if I want to find the total for this point here, we could call this the contact point. For this contact point C, what we have is a center of mass pointing in this direction, and then we have, pointing back in this direction, a tangent. And that means that the total, v total, is v center of mass plus v tangential is actually 0 at that one point. Now, what's so interesting about the fact that this sum gives us 0? Well, it means that the one point that's in contact with the ground has a velocity of 0 with respect to the ground. So why might that matter? Well, let's consider friction. If I have a velocity of 0, then what kind of friction am I using? Well, my options are static friction, that is force static friction, which is less than or equal to the static friction coefficient times the normal force. Or I could have the kinetic friction. So kinetic friction is just equal to mu kinetic times the normal force. But the key thing here is that we know that the static friction's coefficient is larger than the kinetic friction's coefficient, which means that the static friction can give us more total friction force than the kinetic friction. That means that if you're rolling without slipping, you end up with the biggest possible friction force. That's the biggest force to help accelerate you if you're using that force to accelerate. That may be because you're accelerating in a car around a curve. It may be because you're accelerating by braking, like you're decelerating. It could be that you're accelerating by speeding the car up. Rolling without slipping gives you the biggest possible acceleration. That means that, among other things, we make anti-lock braking systems for cars. Why is that? Well, because if you slam on the brakes and they lock and your car starts skidding, then you go from having static friction to having kinetic friction, which also means that you have less force to slow your car down, which means that you suddenly have a longer stopping distance, which means you're actually more likely to hit whatever it is that you're braking to avoid hitting. Likewise, if you're going around a curve on a road and you start slipping, that's skidding out. That means that you have even less control then and are even more likely to fall off the road, like essentially fly off the road because you're not staying on the curvature of the road anymore. So this rolling without slipping condition basically is in some ways like the best condition for control of your vehicle, for best braking, also for best acceleration. You get people who say, okay, I'm going to leave from a parking lot by peeling out. Well, when they peel out, they're not rolling without slipping. They're actually getting slippage at that moment, and so they have a lesser acceleration out of the parking lot than if they simply left rolling without slipping. Now, it's worth noting that there are some types of motion that are, we might call like semi-rolling without slipping conditions. For example, if I happen to have a pulley, so this is a pulley, and I have a rope that is wrapped around and around and around the pulley. So maybe it's more like a rope that's wound around like a shaft on a rod, and then I have a mass attached to one end, and the mass begins to fall. Essentially, as it falls, it puts a torque on this system, which is going to make this have to rotate as this thing falls. If this is radius r, then the speed at which this thing is falling at a given time, v, must be equal to omega, the rate at which this system rotates, times r. So this is sort of like a rolling without slipping condition. It's more of like an unwinding condition. You should be aware of it though, because there are many problems in physics that make use of this condition. That's not technically a rolling without slipping condition, but it's close to it, and the same basic approximations come into play, or the same basic assumptions come into play. So that's all that I'm going to do in today's short video. Hopefully you've learned something from it, and as always, thank you for watching.